Hey everyone! So today we're going to start our new unit, circular motion, and we're also going to talk about gravitation while we're at it. Now I do want to preface this video by stating I did not create this PowerPoint. I actually have it cut off here, but it does state in the PowerPoint that I'll post online that this was created by someone named Martin Kirby. Excellent, really neat. I couldn't not use it. This presentation did come with our new textbook system, which is pretty cool. But moving on. So we're going to talk about circular motion. So circular motion is just an object moving in a circle. If it's moving in a circle, we call it circular motion. Right? It's pretty straightforward. Now, there's a subset of circular motion called uniform circular motion. So this is circular motion where the object's moving at a constant speed in that circular path. All right. So the word uniform meaning constant. And there's the bell. All right. So for the majority of this unit, we are going to be focusing on uniform circular motion. So pretty much the remainder of at least this video today, we're going to be focusing on uniform circular motion. Right. So my first question for you guys is, if for uniform circular motion, does this mean that we have motion with a constant velocity? Right. So does this ball here in this really neat moving, I got GIF, I guess. Anyway, does this ball have a constant velocity? Well, we know that speed is a scalar quantity, right? So that means it only has a magnitude. It doesn't have a direction. So the speed is constant. It's a constant 2 meters per second. But velocity is a vector quantity, so it has magnitude and direction, right? So our object here is actually constantly changing direction, right? So therefore, the ball's velocity is always changing, right? So it's something to be very careful of. It's common a misconception to say, oh, it's moving with a constant velocity. It is not, right? The velocity is always changing. So you can see here, we can draw a vector representing the velocity for this object at any moment in the circular path, right? So here we kind of chose 4 different locations, and we drew the velocity at that specific moment. Effectively, we drew the instantaneous velocity vector for that moment in time. So you see here that path is circular, so therefore, if we draw a tangent vector effectively to that circular path, it's going to be the velocity vector. All right. Now, what we can always see that since velocity is constantly changing, that means that a ball with uniform circular motion, it is always accelerating, right? So remember, acceleration is change in velocity over time. Well, at any 2 moments in time we analyze the object's motion, it has changed its velocity. So therefore, it must have accelerated. And here it actually is accelerating throughout its circular motion. Right? So it does not have constant velocity, it is accelerating. So what is the direction of this centripetal acceleration? Ooh, using a fun word here. I'll talk about that later. But what is the direction of this acceleration? So let's suppose we look at 2 different moments in time. So let's say 1 moment and then the next. So we'll call one be initial, the other one be final. Why not? So we drew the velocity vectors here. So these velocity vectors have the same magnitude, right? Because it's the same speed, but they have different direction. All right. So we can do a couple things with these vectors, right? Usually with vectors, we like to add them, right? So if we added the vectors, we would see something like this happen, right? We're using the tail to tip method, and it would lead us with the resultant vector, which would be the sum. So adding up the final velocity plus the initial velocity. Right? So that's something we can do. Something else we could do is actually subtract these vectors. Right? So we could take the final velocity vector and subtract the initial velocity vector. So something to note is subtracting the vector is the same thing as adding a negative vector. So basically it's the vector but in the opposite direction. So what I mean by that is this here. Right? So subtracting to the 2 vectors, right, we're just changing, let's say, the initial velocity to be in the opposite direction. Right? So moving that to use the tail to tip method, right, we can then now draw a resultant vector. And we see here that a resultant vector, which is actually delta v, right, because it's our final velocity minus our initial velocity, is pointed in this direction that's shown with the blue delta v vector. Right? If you kind of look at that compared to our circle there. Well, that's pointing towards the center of the circle. Right. So one thing a corollary, so the reason why we're focusing on delta v here is because, well, we know that acceleration is change in velocity over time, delta v over delta t. So we see here that delta v is pointing towards, in the same direction that this delta v vector is pointing in the diagram, and delta t doesn't have a direction. So with vectors, if you take a vector and divide by a scalar, which is what time is, it's a scalar quantity, it does not change the directional, it has no effect, right? So vectors can change direction if you're multiplying them in certain ways effectively. All right, so here we're not dealing with multiple vectors, it's just one vector quantity, we're dividing by a scalar, so therefore the acceleration points in the direction of the change in velocity. All right, so what's really neat there, well, this velocity is actually pointing towards the center of the circle. All right, so just to note, this is when we're talking about uniform circular motion. So when our velocity, our speed is constant. All right, so if the object's moving around the circle with a constant speed, the acceleration points towards the center of the circle. Super important. That will almost definitely be tested on not only my test, but on the AP exam. It's a common thing just to think incorrectly. But the acceleration points towards the center of the circular path when we're in uniform circular motion. All right. So something else I want to kind of mention here before we kind of finish up this quick video. So objects in uniform circular motion accelerate towards the center of the circle. We already said that. So you can kind of see here, we've drawn a diagram here. So we have an object of mass m that's moving in a circle of radius r, and I've drawn, I keep saying I did not make this PowerPoint. We have drawn here a couple of different velocity vectors for certain moments in the path. All right. Now we do have a formula for centripetal acceleration, so if we want to compute the magnitude of this acceleration, it is equal to v squared over r. So I was going to say at any moment in the object's path, but the speed's the same. So we take the speed and we square it and divide by the radius of the circular path. And that will tell us the centripetal acceleration. This formula is on your formula sheet. They just write a with a subscript of c, meaning centripetal. And that's equal to v squared over r. Now, I have been using this word centripetal, right? So we've got kind of two words we use in physics with circular motion, and that is centrifugal and centripetal. So centrifugal is a word that we actually won't be using much, if at all, and I'll actually mention more about that later. But centripetal literally it comes from is it Greek? I honestly don't remember. Maybe it's Latin. But it comes from the words meaning center seeking. So centripetal means seeking the center. So the acceleration is pointing towards the center of a circle. So in our diagram here of the object moving in a circular path, right, at a certain moment, so let's say right now, we've got velocity pointing straight to the left and acceleration pointing straight up because that's pointing towards the center of the circular path. Alright, so this is where we're going to stop in the video lesson. If you go to my next video, I'll actually do a couple of examples in terms of computing the centripetal acceleration. So if you note here, I do have a formula up top with force. I will cover that next lesson where we're going to talk and focus about dynamics, the dynamics of uniform circular motion. Alright, thanks for listening.